Hello everyone. Thank you for joining in this YouTube live stream. Here is Agnes from EMPA. I recommend that you watch first the video that we prepared for you with the introduction of the technology that we are offering in this project. You can click in the information box below to find the link. The video lasts about 9 minutes, and then we will meet afterwards for a Q&A session in this live stream. Enjoy the film. The models that we are developing at EMPA, they are basically simulation tools that one can use virtually without having any prototype made. So we can think about fabrics, think about designs that we want to use and applications, and try them out fully safely without investing any money, any time, because it's very short period of time that you need to do this simulation, and try it out first fully virtually in the computer. The principle of modeling that we are applying here is to connect several different models developed by other researchers, but also here at EMPA in-house, in a series of models that communicate with each other in a real time. So to the series belongs human thermoregulation model, thermal sensation model, and model of the clothing that includes all the physical phenomena that occurs within the fabric, but also in the air layers underneath the clothing.
A model of human thermoregulation considers different layers of the human body, which are bone, fat, muscle mass, different skin layers, which have different properties, thermal properties, which in the end affect the heat transfer within the layers as well as on the surface of the different layers. Based on the heat transfer within layers and the interaction between the layers and its environment, we have thermoregulatory responses. The basic principles of human thermoregulations is to maintain the core body temperature between 36.5 and 37.5 degrees Celsius. To do so, he has different responses. So there is on one hand vasomotion, so he can increase or decrease perfusion in the segments of the human body in order to increase heat loss or to decrease heat loss. If we get too cold, we start to shiver, which is like heat production by muscles. And when we get too hot, we start to sweat. So we increase heat loss by means of evaporation.
Thermal sensation model is a kind of statistical model developed on a large database of data from human studies, where people were asked how they actually feel in different environments. So different models are available from literature, and we try to apply them. So we are using the physiological data that we obtain from thermoregulation model to attribute them to actual thermal voting. So the clothing model that we developed here at EMPA consists of the model of the fabric, meaning polymer or natural materials with air between the yarns. And the second very important part of the clothing model is simulation of the air layers underneath the clothing. Since air is a very good insulator, that means that it provides bulk of thermal resistance of the clothing. So fabric actually has a quite small input to overall thermal resistance of clothing. Air layers under clothing can be determined in different ways. The first, more experimental way is to use a mannequin, dress it with the clothing, do the 3D scan of that mannequin, and do another scan with a nude mannequin and superimpose these two pictures, and then we can obtain the distance between the body and the clothing. However, for that, one needs already a prototype, already clothing. A more virtual and faster way of doing it is to use 3D try-on software. For example, there are several commercial softwares available on the market where we can create 2D pattern virtually, put it on the body and bring the body to move. So we can export then body and the clothing already draped around the body and work with that avatars and obtain the distance between the skin and the clothing. So one of the practical applications where we used our model was developing of the ski jacket with our commercial partners, where the task was to determine where panels that are transporting liquid moisture to the outside of the garment and keep you dry and warm should be placed, and what other conditions should be fulfilled so that the sweat moisture coming from the body during skiing comes to the inner surface of the jacket and condensates there so that it can be transported by the active panel to the outside of the clothing. So the mannequins that we have in our laboratory, they have a human-like shape, anatomic shape, like the full body mannequin or the foot or the head mannequin. They can be placed in realistic conditions in a climatic chamber, and some of these devices they can even move in a very human-like manner. For example, walking, like in case of foot mannequin or a full body mannequin.
With thermal devices, we can mimic the human body by the means of heat production. So with activity, the body produces heat, and this can be simulated by such kind of devices. Furthermore, we can look how skin temperature, how the surface temperature of the device changes based on this heat production, and this somehow mimics the change of skin temperature as well. Finally, we are able to apply clothing layers as well on these models in order to investigate how clothing layers affect heat loss and heat gain. In addition, we are also able to simulate the effect of sweating from the human body, which is perspiration from the model to the fabric layers, to look at the moisture transport and how it affects the cooling of the body. And we can look at movement patterns as well, so how movement affects air layers within the clothing systems, and in the end how this affects insulation of the clothing.
We have the whole family of different thermal mannequins that we are using for different purposes, starting with head mannequin, foot mannequin, hand mannequin, torso mannequin simulating a human trunk, and ending with a complete body mannequin with anatomic shape. Head mannequin is used mainly for testing headgear, for example motorcycle helmets or bicycle helmets, as well as any headwear that is used in cold environments. We can place also our head mannequin in a wind tunnel to simulate high wind speeds, like for example in case of riding the motorcycle. Our foot mannequin can simulate walking movement with a realistic pressure exerted from the ground, and we can test with that distribution of moisture and distribution of pressure in the shoe and its influence on its properties and thermal sensation while wearing these shoes. We also can test socks and other devices that are used on the foot or close to the foot on the leg. The torso device is used for testing different fabrics and structures that can be used on the main body of the human. We can regulate air layers so that we can test how the garment should be fitted to the body to optimize its thermal performance. Finally, the full body mannequin is used for testing final prototypes that are made for human use. And this is usually used to confirm if the prototype is functioning or to compare the new product with competitors that are already on the market or with the previous products and see if the performance is improved. And this testing is usually the final stage before we test it with real people. Hello everyone, I hope you are back to this live stream for our questions and answers round. I hope you enjoyed the video, and if you have any questions or need for clarifications or any ideas, please type the question in the chat, and as soon as it pops up, we will try to answer those. Maybe in the meantime, I can still give some words on how you actively can make use of this technology offered in this project. Basically, if you have an idea of the concept, and this is not only involves the aesthetic side of the design, but also functional side of the design, where the garment or whatever wearable thing you are thinking of should interact with the human body, should measure any reactions, or should give a sign back to the body. You can actually test it virtually before actually you develop any prototype. And you can pre-screen physiological reactions in given scenarios to be sure that you already start with relatively probable solution for your functionality of the design or of your concept. The other part regarding mannequins is related more to testing the prototype. So in this moment, you already have something ready, which can be applied on one of the mannequins that you could see. These mannequins can be set to very close to end user conditions with sweating, movement, activity, skin temperatures. And based on that analysis, we can also compare it, check the performance or compare it to anything you would like. For example, up-to-date solution and how much your solution is a completely different or much, much better idea. So please do not hesitate to pop any questions if you have. It seems there are not too many questions. Maybe I will entertain you a little bit longer with different information. Oh, we have something. There is a question. Maybe you tell us, how do you want to work with the artists? So here we have two possibilities. Either we start to collaborate together at the very early stage, at the stage of the concept, where you don't have anything, you have only some drawings and ideas, and we try to think about application scenarios, and we test it first fully virtually using our models. So the technologies that we are using, we are putting a human factor in the middle of the design. So meaning the materials have to serve a purpose of the human body or human comfort or human well-being. So you can actually test at the very early stage, conceptual stage, if your design could be optimized already with the knowledge that we already have about human physiology, human thermal comfort, clothing behavior, basically, or physical processes in the clothing. So does it really allow your skin to feel good, to let the moisture out, and so on, and be comfortable as an overall design? So That is one part of the collaboration that I can very well imagine for quite many concepts. The second part is at the late stage when you already have a prototype. Maybe you have not one prototype, but two or three, or you have questions about which design would be better or more better performing on the human body in terms of thermal comfort or physiological interaction with the body. And here come the actual testing equipment where we can think about scenario and put that prototype on top of it and measure performance according to your questions, and then compare and make the decision with you which option is better. I hope that answers the question. We have another question from Petra Meyer. Can you also use natural material or just materials artificially produced? We have databases for every material that is commonly being used. If it is something that is not very common, like special new kinds of polymers and so on, then we have to characterize it beforehand. But for majority of natural materials like cotton wool or bamboo fibers and other you can imagine, this we have in our databases. So this should not be a problem at all to work with those materials in our modeling tools, as well as obviously with testing on the mannequins. Any other questions? Basically, this technology should help to make sure that the new design is compatible with the human needs for comfort, for wearing comfort, because the acceptability of the design may play at some point quite important role. So these tools will help you to take care of that aspect of your design. And if your design is focused on functionality, this might be a major tool to help you to optimize your design and to target the need or your question that you want to answer with your design. So some examples that we've done in the past, we were optimizing design of skiing jackets so that the moisture can be taken away from the body. We were also working on development on fabric structures that would keep you dry and warm in winter and cool in summer. We have been integrating different type of sensors into typical garments like t-shirts or jackets for monitoring body functions. This is more in the area of medtech, but could be easily applied also for any other entertaining or functional applications. But I see there are not more questions coming, so I would like to give it over for the next informative session with Profactor Technologies on Polyjet of conductive materials. Leo, are you ready to take over?
Perfect, thanks. Hi Fox, this is on Polyjet printing of conductive materials and how we are dealing this in Profactor. Again, sorry for the delay due to some technical difficulties, and I hope I can here now serve you a better job. For those of you who were already there yesterday, this will sound a little bit familiar, but nevertheless, like we did yesterday and also in the morning and in the previous session, please follow the YouTube link to the video. We prepared here a nice insight on how we print a small printed circuit board. It should just be for your entertainment. So Let's watch it and let's come back in 3 minutes. So let's say 11:10 due to the technical difficulties. Enjoy.
Hi to everybody, here is Pavel from Profactor. Hopefully you are hearing me also. Can you respond please? At least Leo, can you say something?
Yeah, I can hear you.
Perfect.
Okay, back to the question and answer session. I hope you enjoyed the video. Let me comment here a little bit. As you saw, it's on Planner. This is due to the fact that we just tested out several kind of materials and possibilities. But the major message we want to provide you is that we can print on the tray, get it conductive on the tray, and place some functional parts like LEDs on that, so that there is basically nothing else there. And we're currently working on testing at least the base to integrate it to a textile. As I see, we have already a first question from Le Grand Tour. If we have a system to check static electricity in the garment. To be honest, no. Unfortunately not. The only thing we could do is somehow check if we see here conductivity via multimeter, but nothing specific here. So I think this will not work that good. So I hope this answers the question. Also, maybe a comment again with the bridge to the session yesterday about Polyjet printing, as this session is also kind of related to Polyjet as the name suggests. But here you see a strong link to or gives a good example of the interplay between the hubs. So the hub 4 is the additive manufacturing hub. In hub 5 we have the cradle from analog to digital. So this means we go here from We all deal with printed electronics here, and tomorrow is the Hub 6 dealing with indeed integration and sustainability and so on the eco aspects. Of course, Polyjet is there everywhere in the Re-FREAM project, I would say, and therefore we splitted this into these individual aspects. Of course, if you have questions related to, let's say, the organizational stuff of the project and so on, please refer to the help desk. You find here also the link below, and I think also in the description. But feel free to ask now in the next 10 minutes still left there. Question from Petra Meyer is, how do you involve this technology into natural material or clothes? There can be several aspects to that, or several strategies to that. The first one is kind of the natural, as you might have seen in the video, that we print or we built the project layer-wise. This means we could start with the clothing and print on it. There are also strategies to directly create, let's say, a clothing out of Polyjet and integrate it directly there. So here you see this could lead into a higher complexity in building the object or building the fashion piece. But these are the two aspects that come to my mind now immediately. Natural materials, I think you also mean, let's say, bio-based material, biodegradable material, can be integrated, need to be tested for sure. Therefore, we are here the scientific technological partner to test things out in advance as well. And to give you a little bit of insight, the first thing is to try to print the material on something in this aspect. So when we have, just an example, a wooden piece, we try to print the conductive material on it, try to sinter it. That's also one key aspect in enabling here a conductive path, and see how it behaves, if the natural material can withstand the sintering conditions, or also the compatibility of the material itself. Just a little bit of insight with not much going into the detail. I hope this answers the question to your satisfaction. Are there further questions? That's one tricky question. Cost relation. So Petra, about the costs and the prices. This is sure strongly depending on the model, on the piece you want to produce. Speaking of material costs, we are currently using silver-based inks for integration and establishing the conductive paths due to some, let's say, technical reasons, and of course the sintering conditions are there, moderate and good to handle. Pricing about that, it's not really cost effective, to be honest. There are cheaper ways to do it. There are more expensive ways to do. Since we are aiming for, let's say, lot size 1 up to, let's say, 10 or 20, this is one cost-effective way to produce. If I'm thinking about mass production or going into mass production, Polyjet might not be the best suited at first sight, but considering the individualization aspect and highly integratability, then we are back here on the one technology or one of the few that can indeed serve the job. About the testing and corresponding models, yes, that could be true, because then we know what is aimed for. So always with Polyjet printing, and especially in this case, we need to know what kind of material we want to print on, and so on. Within the Re-FREAM project, just to mention that, the material aspect and paying for the material is a thing. Please refer here to the help desk for, let's say, better answers to that, how to deal with the material aspect and the cost aspect in the project. Yeah, a sample would be helpful.
And maybe I can tell something to this, to the question of Petra Meyer. If we need samples, yes, because the textiles are different, and we usually have to planarize the surface of the textile to be able to print on it without soaking the conductive material into the textile, which then somehow reduces the resolution of printing, for example, for integration of electronics. So it's definitely better to send a sample to us, and we can try to do a test print on it.
Question from Tessa. Yes, we have experience on printing conductive material on textiles. However, as Pavel already mentioned slightly, soaking in to the fabric of the conductive material is a challenge. To overcome this, we have here some solutions and some experience on that. Yeah.
So the question of with sense design about sustainability, this highly depends on the design. We can print, let's say, the area of 40 by 60 in principle, but we can also print just small modules, small pieces of textile with the electronics itself, which has rivets or pins on outside, which then we can put on the textile and remove it before washing. This is in principle possible, but this should be also discussed probably with colleagues from IZM Fraunhofer, Berlin, because they have, let's say, more developed technologies to connect the piece which can be printed by us to the rest of the textile, for example, to connect more electronic modules on the T-shirt, for example. So the question is about how to develop the technology for connecting our printed modules on small pieces of textile to the rest of the garment, for example.
Question from Tessa about printing with conductive flex filaments. I think that here to clarify here is a good idea. Polyjet is a printing platform based on inkjet printing. So it's basically the same as your office printer or your inkjet printer at home. So you fill in a low viscous ink and print it to some print heads, and you generate here then in 3D your objects via UV curable polymers. So printing with filaments is kind of obvious that this is not possible with Polyjet. However, a conductive flex filament, I think you refer to something like fine deposition modeling, so FDM printing, or as it is often called, FFF printing. We personally don't have experience with that, but I think you can refer to Haratech in Linz. Petra, what you mean by natural inks? Can you be here a little bit more specific, please? The limitation for Polyjet printing, to take this up, is that you need to have a low viscous ink. This means that we have a certain viscosity range where the ink can pass the printhead. That's basically the only limitation. So yes, if this natural ink fulfills this, then we could print it.
I want to add that also particle size.
Exactly.
So the particles, if the ink contains particles, for example, graphene or silver, like we use, has to be small enough to get through the inkjet nozzles, which are in the printing head.
And if you want to know how big this viscosity range is, you can, on the one hand, look it up at the Stratasys homepage, or in some other documentations, it's in the range of 15 to 25 millipascal seconds. That's the property, the key property to know. Particle size is allowed. Pavel, you know by heart?
Yeah, it's in the range of hundreds of nanometers, because the nozzle diameter is tens of microns, and the particle should be at least 10 times smaller. And also the particles should not agglomerate, so not to create big clusters, because also the clusters can clog the nozzle. So it should be homogeneous dispersion of nanoparticles, basically.
Yeah, so when you have particle sizes in the area of 100 to 200 nanometers, you're fine. 1 micron is already a challenge, so this can cause serious problems. Okay, I think we are now getting to an end. Since the session, I think originally I think it's until 11:30. If not, then I hope you enjoyed the additional time. I'm not so sure about if it's 11:20 or 11:30. Nevertheless, I hope you enjoyed the session from analog to connected of the Re-FREAM project today. And it continues tomorrow with the hub from Valencia. And until then, thanks for your questions. And I hope we read or hear from you in the future. Okay, so again, let's say bye to all of you. It was a pleasure to discuss a little bit.
Thank you for your attention. Bye-bye.
And see you soon. See you tomorrow for some of you. Bye.
Bye.